The Prony method is, it was introduced by Giuseppe Prony in the 1700s, in which he made an observation wherein the exponential expansion of gases was modeled as a system of linear equations by his insight. He, essentially constructed a model wherein autoregressive model wherein the further observations were were taken as a assumption to be evolution from the previous values of the observations, and T-Plit's matrix was constructed. So just a brief preview into what I'm going to be talking today at this time. So my talk is entitled, and I have adapted the Prony method computationally, in which the Prony method is very computation intensive, and I considered this problem of the Prony method has to be modified so that the precision of the computation is better. We have some assured lower bounds in the precision of the computation, and so that was the subject of investigation in this study. And essentially, there is a certain nuance or an insight which at least experimentally shows that we can potentially get a higher precision, consistent higher precision with the Prony method. So, having given that brief preview, let me talk about today's agenda, which is I'll start with the introduction. Let me move this. I'll start with the introduction, then I'll discuss the context and of the current work in relation to recent literature on the Prony method, and I'll mention the scope and significance of this work, and I'll mention the fundamental premise which leads to the assured, consistently assured lower bound on the precision. And that is the nuance of this work, and so I'll also mention in detail how the methodology that is suggested is employed in the Prony methods adaptation, and then I'll briefly touch upon details of hardware and software that were used for performing this experiment and making the observations about the results that emerged, and we'll essentially define the metric that gives the indication of the lower bound, consistent lower bound in the experiments output. And with that, I'll conclude the work, present the experimental results, and conclude the work. So that's today's agenda for this session. As I mentioned, dwelling into the introduction, is not moving. Why? Why is it not moving? Sorry about that. Let me stop and reshare. Okay. Yes. So here we go. The Prony method for approximating signals comprising sinusoidal exponential components is known through the pioneering work of Prony in his seminal dissertation in the year 1795, as I just mentioned. But real-world application required that the heavy work of the computation, be delegated to the modern digital computer. And however, the cornerstone of the method is to set up the autoregressive model, where the subsequent values of the input signal, as I mentioned, are assumed to depend regressively on the prior values, and then solve the model by dividing the Toeplitz matrix with the input signal and obtaining the remainder to obtain the autoregression coefficients. Now, once the autoregression coefficients are obtained, the characteristic polynomial is solved, for the roots, and the roots give the damping factor and frequency of the output signal, which is the approximation, the Prony approximation, or the Fourier approximation of the original input signal. And once those are obtained by substituting back into back propagation feedback sort of methodology used to put the roots obtained into the original Toeplitz matrix and as knowns, and again obtain another set of equations to solve, which gives the amplitude and phase of the approximating. So essentially, we have extracted the frequency and phase and the amplitude and the damping factor, all the four factors that characterize the output signal, which is the smoothened version of the input signal. So having said that, I'll go ahead and mention what is there out there. From the 17th century, when Prony actually introduced the method, in the recent times, there have been attempts to comprehend, adapt, implement, and optimize the Prony method with modern electronic and computing platforms doing the heavy-duty tasks. These adaptations take form of varying the parameters in the core Prony algorithm. That is one obvious. There is literary work that points to that, and I put that in the references. And this is done with the optimization in perspective. So vary the core parameters and get an optimized computation. Other variants include, trying to get the intermediary output for use in related settings from the core algorithm. Again, there are references to this and these, and I've put them for ready reference. Yet another adaptation is, for utilizing the transformative power of the core algorithm in the codomain, and thereby the ease of scientific analysis. However, in all of these works, consideration has not been given to the precision with which the results are obtained, so that the output signal has to be a close representative of the input signal with the limited computing capability. You don't have infinite what you call the computers don't have capacity for infinite precision. So there has to be an assured lower bound that needs to be found for precise computation, so that the output signal matches the input signal closely, as well as the algorithm converges within the specified time and resource constraints available. So having said that, this has a lot of consequences in critical applications, biomedical applications, and power signal applications, and so on and so forth. Having said that, let me go ahead and mention the scope and significance of this work. This work, as I mentioned, is focused on obtaining reliable bounds in the computational precision of the output from the Prony method. Reliable bounds in the computational precision of the output from the Prony method. So the bounds are so obtained are significant in practical applications, as I mentioned, and the level of precision significantly impacts the ends for which the method is used. For example, the monetary cost effectiveness in case of power systems, and the effective diagnosis in the case of biomedical engineering. So this work is unique in that though works with similar objectives exist, the premise and methodology described here are not found in existing literature. And we'll see the nuances of the methodology which lead to that insight and implication. So what is the nuance of this method, this particular adaptation of the Prony method? The implementation of Prony's method in MATLAB, I put a reference to that, in this adaptation of the Prony method, the coefficients of the characteristic polynomial computed in the first step autoregressive model are self-adjusted by a constant multiple of the standard deviation of their own values, and this assuredly compensates for the imprecision in the computation due to the computing device limited capacity to perform the computation to an arbitrary precision. What essentially that means is that this is an observation like you have a limited computing capacity, and within that computing capacity you want to extract assured level of precision in the output signal. And the observation here is that the coefficients obtained in the first step in the autoregressive model, as I will mention in the further, these coefficients can be adjusted by their own standard deviation, and that as experimentally proven gives higher precision in the output in the matching of the output signal to the input signal. And so that is the nuance. Let me go ahead and describe the method in detail and mention where this nuance is introduced in the method. So having said that, here is the methodology that is basically in this adaptation of Prony's method. So step number one, this step consists of setting up an autoregressive model with the random sample observations, where the assumption is that the observations are naturally organized such that the nth observation is linearly dependent on the n-1 preceding observations, thus yielding a model which regressively relies on computing the Toeplitz matrix set up to relate those observations in accordance with the above assumption. Now, once the Toeplitz matrix is set up, solve the above model, yielding the coefficients of the Prony characteristic model, a characteristic polynomial, which is prerequisite to obtain the amplitude and frequency of the final approximating signal as yielded by the polynomial roots. Now, once you have obtained the coefficients and you solve for the characteristic polynomial for the roots, you essentially get the amplitude and frequency. But the nuance in this particular adaptation is that you, as I mentioned, adjust the coefficients of the characteristic polynomial by a standard deviation of their own values. This work proves that this adjustment helps overcome the computational imprecision introduced due to the limitation of the computing device's arbitrary precision arithmetic. Now, in step number 4, work with the adjusted polynomial coefficients to obtain the amplitude and frequency of the output signals, and also computing the damping factor and phase by substituting back, as I mentioned, into the original P-Plix matrix and finding the roots again in the original equation. Excuse me. So step number 5. So how do we quantify and mathematically, or have a metric by which we can say with scientific certainty that indeed this nuance is an improvement over the original Prony method for yielding consistent lower bound in the precision. For that, we introduced the precision metric, and I will mention the metric which has been used, and mention the results where the metrics values that were obtained for the different set, number of input samples shows consistently that they yield a constant value of the precision metric. Having said that, let me go ahead and show this is just a brief review into how this was actually implemented in MATLAB. And that's a screen capture showing MATLAB in action. So having said that, I'll mention the hardware and software used. The hardware was this very PC 64-bit with Windows 10 operating system, and the software was the MATLAB release 2024A, which was used for performing this experiment and obtaining the results. So as mentioned there, we have the precision measure, which I mentioned. Now this precision measure, you see n is the sample size, and the norm of the reconstructed signal with respect to the original signal divided by the norm of the reconstructed signal with respect to the mean of the original signal. If you closely visualize this second expression right here is nothing but the number of signals that were not precisely recovered from the original signal. So and n is the sample size. So subtracting this number from n actually gives how many signals were exactly recovered from the with the lower bound on the precision from the original signal. So that is about the metric that was used to quantify and understand the results which were performed through the experiment and the adaptation of the Prony method. So the experiment results yielded the fact that when the input vector size is 100, and the coefficient adjustment factor, which is nothing but what we introduced as a nuance in this adaptation, when there is 1 sigma of the coefficients, you obtain a precision measure, which we defined just a minute ago. We obtain 90 as the value. And you see that with the increase in input signal size from 100 to 1000 components and a 10 sigma adjustment of the coefficient, again it is in the order of 900. And when the input size is increased by 10,000, and we have a coefficient adjustment factor of 100 sigma in the computation that we perform, then the assured minimum empirical guarantee is that we'll recover 9,900 of those signals. And this was proved by several iterations of the program on the different input sample size. And the only insight that we have is that internally the processor is organized such that for performing a certain computation with a certain precision, the aggregate is that the standard deviation of those values itself is the precision to which the computer can perform that computation, and hence this observation right here. Having said that, I'll conclude and mention the future work possible. So this work has proven with the adaptation of the Prony method set forth by the author, there is a consistent improvement of the lower bound in the recovered signal precision, thus improvising the Prony method for advanced use in diverse and sensitive fields such as medical engineering and electrical power systems. As I mentioned early on, just reiterating the same fact. The biomedical applications include improvement to disease detection, and further works on this are possible by signal analysis, and I put a reference there for convenience of better understanding. There is a scope for rigorous stability analysis of the recovered signal, and I have a little bit of an insight into that, which says that the stability analysis of the recovered signal is better with this adaptation, and there is a rigorous methodological reasoning by which I'm projecting that conclusion. Also, there is some scope to apply this work in the realm of quantum computing to evaluate whether the same empirical results are upheld in that realm as well. Having said that, I've put some references here for ready reference. And once again, thank you.